Welcome to the study of gas laws. I have some certainty that you have done some gas law work in your previous course, and so this will be, for many of you, for much of this, a review. Maybe not all of it's a review, but gas laws are pretty intuitive, pretty easy to understand, and so I'll do my best to walk you through this pretty quickly and efficiently. As always, jot down questions as you're listening and bring them to CCL. So one of the properties of a gas is that it exerts pressure in a container or against the surfaces that it comes into contact with. Often that is in a container, like in the balloons in the photo. Pressure is defined as force per area, which is why, at least in the United States, we have a unit called PSI, pounds per square inch, that is used to do tire inflation pressures. Okay, so if you look at the side of the tire on your bicycle or the tire on your car, or perhaps even at a basketball or a volleyball or a soccer ball, there's probably a PSI value there to tell you the appropriate pressure to put into that tire or that ball. We're not going to use PSI. We are going to use millimeters of mercury, and we are going to use atmospheres. 760 millimeters of mercury is equal to 1 atmosphere. We also have a value of 101.3 kilopascals, but I don't think you're going to see that very much, so we'll stick with these 2 units throughout this course. And these 2 units can be converted by using a 1 atmosphere for every 760 millimeters of mercury, or 760 millimeters of mercury for every 1 atmosphere conversion. I'm hoping you've seen the combined gas law. What do the variables represent? I think that's probably self-explanatory. P is pressure, V is volume, N represents the moles of the gas, and T represents the temperature. Okay? Are there any restrictions on the units? Not really, except for temperature. Temperature must always be in Kelvin. And to convert, use that conversion, okay? There are actually other named laws, such as Boyle's law, Avogadro's law, Charles's law, contained within this combined gas equation, but that's irrelevant. You don't care, doesn't matter what those names are. So let's talk a little bit about the individual relationships between some pairs of variables that are found in the combined gas law. If we want to focus on the pressure-volume relationship, what we would do is remove the moles and temperature from the equation. If they're constant, I can just eliminate them, which reduces my law to P1V1 equals P2V2. This is an equation that expresses an inverse relationship between those variables. As the volume goes up, the pressure decreases. On the other hand, if we look at the relationship between P and T, or V and N, these are both direct relationships, because that's a direct proportion. There are 2 aspects to gas behavior work. One of them is solving the math, which most people find pretty easy, okay, because you're used to using these laws. It's kind of plug and chug. And the other is explaining the behavior. Keep in mind, explaining is just as important as calculating. So as we talk about these things in class and as you do the reading, focus as much energy on the explaining as you do on the calculating. This is an example of a typical problem that requires you to use the combined gas equation to solve for the requested variable. So take a few minutes to read this question over, pause the video, see if you can solve this in your notebook, and then you can turn it back on and I'll show you how I approached it. So the first thing to do would be to read through the problem and evaluate all the given information, and that's what I have done here. I've labeled it all up. The next thing I do is set up my equation and rearrange it. I rearrange before I put the numbers in, which I think is a little easier. Maybe you don't agree. As long as you can do it correctly, it doesn't really matter to me. I also assumed that the moles was constant in the balloon, and that the amount of gas in the balloon doesn't change. Now we plug the values in. Once you've plugged the values in, you will be able to see that the units will cancel beautifully. Kelvin cancels Kelvin. The unit left will be liters, which is appropriate, and then you pick up your calculator. You can certainly check my work, but I'm getting 8.2 liters for the volume. So that's how I would solve this one. There's another law called the ideal gas law, which really is one and the same with the combined gas law, and you can kind of see how we can start with the combined gas law and end up with this law here for the ideal gas law. This is one with which I hope you do have some experience. This is very useful when we're solving for a gas at a single set of conditions. Okay, you notice there's no 1 or 2. It's not first pressure, second pressure, original volume, final volume. Just one of each value are present in this equation. There are multiple R values that we'll use throughout the course. The one that we use in gas laws is this one. It's the one with the units that correspond with the variables that are in the Pivnert equation, PV equals nRT, and so that's the one that we'll be using when we do gas law calculations. Keep in mind, though, that the units you're using in your problem must match these exactly, or the constant is not valid, okay? And this is the constant you want to use, so you have to make your units agree with these. So let's take a few minutes and solve this first ideal gas law problem. Just the first one, so pause the video and take a shot at it. And then you can start up and I'll show you what I did. This is how it looks with the equation rearranged. Again, I rearranged before I put numbers in. Plug in those values and then pick up your calculator. And so we found moles, and then using the molar mass, I converted that to the mass of oxygen. Remember that it is diatomic, so I'm using 32, and there you have it. So pause again and take a shot at the second one. So here we have the values plugged in, and again it's now just calculator work. And this is the temperature in Kelvin. Now you can also verify here that the units cancel. And you can see that when I cancel them out in red. So there you go. Another useful number for you to have is this value here, 22.4 liters. This is also on your equation sheet. This is called the standard molar volume of any gas at STP. STP is a set of temperature and pressure conditions that represents 0 Celsius and 1 atmosphere for the temperature and the pressure. And this number is sometimes written as 22.4 liters per mole, or 1 mole per 22.4 liters. And what that can do is come in handy in terms of your doing some quicker calculations than using Pivnert. We are going to get to kinetic molecular theory during the second lesson, so I'm going to not say much about that right here, but this molar volume is an average for pretty much all gases at reasonable temperature and pressure conditions. Keep in mind, though, that if we take the temperature and cool it too much, a gas actually gets closer to liquefying, which makes it less likely to behave like a gas. And if we increase pressure too much, the particles also get closer together and also get close to liquefying. So if temperatures are too low or pressures are too high, these laws that we're talking about may not be so valid. This will not be a problem at all because you will not be calculating anything other than ideal gases. But I just want to point out that if we took things to an extreme and cooled or exerted a lot of pressure on a gas, these laws may not be valid. We're going to do one more quick question before this lesson ends, and that is calculating the density of a gas at STP. At STP, 0 degrees Celsius or 273 Kelvin and a pressure of 1 atmosphere, the volume of a mole of any gas would be 22.4 liters. Okay? So, since density is mass over volume, if we assume that we have 1 mole, then we would get a density of, for this gas at these conditions, 1.25 grams per liter. So, not a hard calculation to do. If you're not at STP, then you're going to need to find the volume using Pivnert. And then do your D equals M over V calculation.